Another exam! Woohoo! Another chance for us to show what we've learned. Ah, how lucky we are. So this is a final exam for the first semester of calculus, our basic calculus, also known as Math 165, fall 2022. A lovely exam. Now it looks like there are 7 questions, but secretly there are 8 questions. Bonus! Woo-woo! All right. Well, that means we shouldn't waste any time. So, of course, we write our name. After all, we want the credit, right? Yes. And let's begin. Number 1. Find values a and b so that the following function is continuous at x equals 0 and x equals 2. Justify your answer. So this is a piecewise function, meaning it has several pieces. We have one behavior below 0, another behavior between 0 and 2, and yet another behavior above 2. Okay, so what do we do? Well, the answer is we just work it through piece by piece. And, well, let's see what happens. Okay, so a couple of key things to say is we say, well, look, what does it mean to be continuous? All right, so continuous says no surprises. So continuous at 0, we need to know that the following happens. Namely, that the limit as x approaches 0 of f of x is equal to f of 0. That's what continuity at 0 means. All right, now notice that 0 is a place where we've split our function into pieces. So in other words, there's one type of behavior to the left, another type of behavior to the right. So we're actually going to have to say a few other things. Now, when we plug in 0, we're going to be in this ax plus b. So we say, okay, f of 0, well, that would be a times 0 plus b is b. So here we have sort of 2 branches. What's the limit as x approaches 0 from above? And what's the limit as x approaches 0 from below? Now, from above is actually, I think, the easier case. Because what happens? From above, we really have the ax plus b. So when we say above, just a little bit. You know, we have 0, and then we're just over here. And so when we're just above 0, we look like a times x plus b. We can plug in, and we get b. Okay, so all right, no surprises. So now we come to this one from the left. I think this is where we're going to be doing our work. So we have x approaches 0 from below of, so we're just, you know, if here's 0, we're just on that side, right? Just below. And so it's 14, x subtract e to the 4x plus 1 all over sine of 2x. Now, plug in 0. We see sine of 0 downstairs. Upstairs, 0 minus 1 plus 1. 0 over 0. What does that mean? It doesn't mean 1. It doesn't mean hopeless. It means more work. And in particular, 0 over 0 is fantastic. So we channel our inner l'hôpital. We can, you know, during the test, we may not be able to do the full thing, you know, you know, you do not need to wear a beret to be able to channel your l'hôpital, but you know the spirit. Okay, so go into 0 over 0. We say by l'hôpital, this is the limit as x goes to 0 from below. Take derivative of the top over the derivative of the bottom, not the quotient rule. Derivative of the top, derivative of the bottom. So that's 14 minus 4 e to the 4x. And the 1, you just go on. Poof. Downstairs, derivative of the sine is, derivative of sine is cosine and bring out the 2. Okay, mon amis. What does this do? You plug in the 0. No more 0 downstairs. Ho, ho, ho. It is complete. So we get 2 times 0 is 2. Upstairs we have 14 minus the 4. E to the 0 is a 1. Don't forget, don't forget. So we get the 5. Ho, ho, ho. Okay, so what do we have? We need to have that b must be 5 and also must be b, and therefore we say, aha, b is 5. Wow. All right, let us take off the L'Hopital hat. For now, we may be coming back. We will see. We will see. Okay, here we go. Now remember, that's just 1 point. We have 2 points. 0 and 2. Oh, okay then. Well, let's go to 2. So at 2, if we're going to be continuous at 2, same process, right? So then the limit as x approaches 2 of f of x should equal f of 2. Now, we know that b is 5, so we can update here. And we say, well, that's plug in 2, because there, see how we have an equal 2? That would be 2a plus 5. All right. Now, again, different behaviors on the 2 sides. Split it up. So, we get the following. Well, we're going to have a limit as we approach from below, and we're going to have a limit as we approach from above. Now, from below, what happens? Well, from below, see, we're below 2. Ah, why did I write 0? Ah, okay, 2, 2, 2, 2, 2. Okay, so below 2, just below 2, we're at ax plus 5. So this is the limit as x approaches 2 from below, ax plus 5, which is the 2a plus 5. Okay, good. Well, that's kind of what we expected. That's where our work will be. Okay, so we say, well, what's happening here? X approaches 2 from above. We'll have 3x squared minus 2x plus 1 over x plus 2 squared minus 25. So you plug in 2. You don't even think about anything else until you say, well, let's plug in. Say, well, okay, downstairs, 2 plus 2 is 4. 4 squared, 16. 16 subtract 25 is negative 9, which means no L'Hopital, because we're not having division by 0. Woohoo! Nice! Yes! Okay, now upstairs. We plug in. 3 times 2 squared is 12, minus 2 times 4, it's minus 4, plus 1. So 12 minus 4 plus 1 is well, it's 9. Downstairs, minus 9. So we see that this limit is minus 1. All right, so again, we need to have that these match. All right, and so, well, 2a plus 5 better be negative 1. We subtract 5. That tells us 2a better be negative 6. Tells us a better be negative 3. All right, good. And we're actually done. But let's go ahead and just put our answers together, and we'll say, okay, a should be negative 3, b should be positive 5. Life is good. Wonderful. Wonderful. Woohoo! Nice. All right, well, on to the next one. Number 2. use the limit definition of the derivative to compute the derivative f prime of x for the function f of x is 2x plus 3. And it gives us this really, you must use a limit definition. And solutions using other methods will not receive credit. Okay. All right. Well, this is sort of to be expected, right? We're really being tested on what's the definition of the derivative, the limit definition. So if we're going to do this, we say, all right, we start by saying, well, f prime of x, write down the definition. Now there's two definitions. I always recommend h go to 0. And the reason I recommend that is when you're thinking about what's going on, normally you'd have a 0 over 0 issue when you talk about the derivative. And so you want to get some cancellation. So it's easier to identify a single h upstairs to cancel. So that's why I like the h definition. Okay, so we're not doing anything with the 2x plus 3 yet. We're just doing the definition here. Even this, we've already gotten a point, at least. See how easy it is to get a point? Now we just have to get the rest of them. Now, here's the important thing. I am now going to write f of x plus h. This is the place where it's easy to make a small mistake, so we're going to be careful here. So what we're going to do is we're going to put a parenthesis. This is our f of x plus h, and everywhere I see an x, I put x plus h. Now, again, using the power of parenthesis. Parentheses are friends. They save us points. We like parentheses. Okay, now f of x, that's easy, just copy. But again, we know parentheses. Parentheses are going to make a difference here. Why? Well, if you expand upstairs, you're going to get 2x plus 2h, because the 2 distributes. That's why we want to make sure we have that parentheses. Plus 3 minus 2x minus 3, because the minus distributes as well. So that's why you want to make sure you get the parentheses in to get all those constants in front distributing correctly. And if you forget them, well, things can go badly. We don't want things to go badly. We want them to go goodly. That's why we're in this class, because we're good people. The 3's cancel. The 2 x's cancel. You should anticipate lots of cancellation. And indeed, the way this goes is if you live a good, clean algebra life, things cancel. Now, after you cancel the stuff without h, you say, aha, stuff with h, I can pull an h out on top, pull an h on the bottom, and this is the limit. As h goes to 0, 2h over h is 2, which is 2. And there we go. Now we can check this because we can say, oh, yeah, the derivative of 2x plus 3 is 2. No surprise. One other small thing I want to point out, and I'm sure you're not going to make this mistake, but notice how we kept writing this limit up until the point when we actually did something. They're going to check for that. So don't be sloppy. Put it in there, be careful, and do your algebra. There's only about 2, well, maybe 3 things that you need to figure out algebra-wise. How to FOIL, how to add fractions, and how to handle square roots. And square roots you use multiplying by conjugate. If you can do those 3 things, you are good. You're better than good. You're great. And that's wonderful. Okay, so we got our points. All right. Now, part B. Find the value of the following limit without using L'Hopital. Oh, no, but we were so good at that. Oh, my goodness. Okay. Hint. Do not evaluate the limit directly. Look carefully at its form. Okay, so we're admiring this as we would a classic Renaissance statue. It's like, it is beautiful, the detail, it just comes to life in front of us. But I think what they're really trying to get us at is they're saying, doesn't it feel like a derivative? Well, it kind of does, right? If you think about derivative, this is the definition would be limit as h goes to 0, f of x plus h minus f of x over h. And we stare at it for not too long, and we say, okay, matching, matching, matching. Say, well, okay, certain things are pretty easy to spot. Okay, limits match. No surprise there. All right, cool, cool, cool. The h, okay, yeah, that's fine. All right. But then we start saying, well, okay, so then if this is f of x plus h and that's f of x, we're like, oh, okay, so this is acting like our x. And then what we have is okay, x plus h, x, and then our function would be what? Well, it would be sine cubed of x. So we have a great aha. This is the derivative. In particular, if this is our function, we're really after the derivative at pi over 6. So I say, all right, we can't use L'Hopital. We don't have to do a limit definition, and because we don't want to evaluate the limit directly. In fact, it tells us not to do it. You know, do not, because they don't want us to. They're really testing on, can we spot the derivative? Okay, so I say, well, I see if f of x is sine cubed of x, f prime of x is 3. Okay, got to do a chain rule here. 3 comes down, sine of x to the 2 times the derivative of sine, which is cosine. So you plug in pi over 6. That'd be 3 sine of pi over 6 squared cosine pi over 6. Now, sine of pi over 6 is a half. And cosine pi over 6 is root 3 over 2. So this would be 3 times a half squared times square root of 3 over 2. And if we multiply that out, we would end up with 3 square root of 3 over 8. And that's it. That's it. So that's that limit. And yes, isn't it nice? That's why we learned all these rules, by the way, so that we don't have to take limits this long way. We can say, oh, this limit represents something, and we have rules for how to actually carry it out. It's nice knowing things. I highly recommend it. 4 out of 5 dentists recommend knowing your derivative rules. All right, well, 2 down. Let's keep going. Number 3, find an equation for the tangent line to the graph of the function y equals f of x that is given implicitly by the formula xy is equal to 2 arctangent 4y at the point where y equals a fourth. All right, now, when we see the word line and we're asked to find a line, we say, aha, we're going to go out and find ourselves a point, and we're going to find ourselves a slope. Those are our 2 main things. Now, we're told the point where y equals a fourth. Now, that's not a full point, but it's part of a point. We still need the x coordinate, but we can get it by our relationship. So we would have 1/4 times x, right, x times y, is equal to 2 arctangent of 4 times a fourth. Now, 4 times a fourth is 1. What is arctangent of 1? Well, that's the same question as saying tangent of what angle gives us 1? A 45 degree. But we're in calculus, so we don't say 45. We say pi fourths. So we say, oh, okay, so this would be 2 times pi fourths. Well, we can multiply both sides by 4, and we see great, aha, x is 2 pi. So our point is at x equals 2 pi, y equals 1/4. All right, so we're part way done. Now the reason I'm saying part way is that's the point. We've got the slope. Okay. Well, as they say, it's all about the slope, about the slope. Yeah, baby. It's all about that slope, about that slope. Oh, maybe. Okay, so how do we do it? What's our technique? There's a clue, a word they gave us here that will key us in. Implicit. So this is implicit differentiation. Now, how does implicit differentiation work? Well, the thing is, y is a function of x. We just don't know what it is. That's the idea of implicit. So what we say, we look at this and we say, I'm going to think of y as being a function of x. I just don't know what it is. And now that I have that mindset, I'm going to take the derivative of both sides. So everywhere where we see a y, we, in our mind, think of that as really y as a function of x. So x times y as a function of x is 2 arctangent of 4 y as a function of x. So derivative on the left-hand side, two things multiplying, product. So derivative of the first times the second plus the first times the derivative of the second, which we will denote as y prime. Okay, that's the left-hand side. And here the key is, I don't know what y is. I don't know what y prime is, but that's okay. I can just say, I denote y prime with this symbol called y prime. Over here, well, we have the 2. Now, arctangent of something. Chain rule. 1 over 1 plus the inside squared times the derivative of the inside. Okay, good. Now, what are we going to do? Well, we're after y prime at our point. So now our next step is we're plugging in. So we're plugging in x equals 2 pi and y equals 1/4. So we have, I'll make a note here, plug in x equals 2 pi, y equals 1/4, and solve for y prime. That is the slope. Cool, 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 cool. Okay, so here we go. 1 times y will become 1/4. X times y prime will become 2 pi y prime. That's going to be equal to 2, 1 over 1 plus 4 times y is, well, 4 times a fourth is 1. So 1 squared, 1, times 4y prime. Well, things simplify, right? The 2 and the 1 over 1 plus 1 will cancel out. And then we can say, okay, well, subtract, subtract. We'll get 2 pi subtract 4 times y prime is equal to minus 1 over 4. Or y prime is minus 1 over 4 times 2 pi minus 4. And if we wanted to, we could distribute in. We can also put the minus downstairs. Say, well, this is the same as 1 over 16 minus 8 pi. It's a weird number. But weird numbers don't necessarily mean wrong. Some numbers are weird. Most numbers are weird, actually. It's kind of a weird mathematical fact that most numbers are weird, even though we tend not to encounter them in our day-to-day life. Okay, so we've gotten our slope, 1 over 16 minus 8 pi. Point slope, we're ready to write our answer. So y minus our y coordinate, 1/4, is equal to our slope, 1 over 16 minus 8 pi, times x minus our x-coordinate. Now, they didn't tell us what form to leave our answer in, which means that's a great form to leave our answer in. Don't simplify if you don't have to. And here, we don't have to. So there we go. Life is good. Life is wonderful. All right, on to the next problem. Number 4. Sand is being dumped at a rate of 12 pi foot cubes, or you could say cubic feet per minute, such that it forms a pile in the shape of a circular cone. So the bottom is a circle, and then it forms this cone, whose height is always 2 times the radius of the base. How fast is the height of the pile increasing when the pile is 4 feet high? Include units in your answer. So for a cone, volume is 1/3 pi r squared h. So what are we doing? Well, we have rates going on. We have the sand is being added. Well, what is that? Well, it's a volume rate. How do we know it's a volume rate? Well, notice foot cubes. That's a volume. Okay, so this is a volume rate. Foot cube, or cubic feet per minute. So we could also say the change in volume over change in time. So what are we after? Well, how fast is the height increasing? So we're trying to find dh dt, which is the change of the height. So we're given one rate. We want to find another rate. It's as if these two rates were related to each other. Exactly, exactly. Okay, so what's our basic setup? Well, we know our volume. Volume is 1/3 pi r squared h. Now, do we know anything about r and h? Well, we know r is the radius, h is the height, but there were a lot of words. And sometimes words are kind of scary. We may shy away from them, but there might be a key here. So let's look back. All right. It forms a pile in the shape of a cone whose height is always 2 times the radius of the base. What is that telling us? Well, it tells us the following. Height is 2 times r. Right? That's just, take that statement, height is 2 times r. Now, I want to end up with a dh dt. So, do I want to replace r or do I want to replace h? And the answer is, I want to replace r because I want everything I can in terms of h. So we could say, oh, that's the same as r is a half h. So updating, volume is 1/3 pi, 1/2 h squared h. Okay, a half squared would be a fourth times a third, gives us 1/12 pi, and then we have h cubed. All right, so we're now ready. We have our variables that we're interested in, v and h, are related. If the variables are related, the derivatives of the variables are related. Because what's going on? Well, what's going on, remember how if you were looking at an earlier problem we talked about implicit differentiation? Well, in this case, it feels similar because it almost is. But now instead of saying v is a function of h, we're really going to think of, oh, v depends on t and h depends on t. So that's what we're thinking. So we're going to take the derivative of everything with respect to time. So we say, okay, so according to this, dv dt, that's the derivative of the left-hand side with respect to t. Well, that's the constant, 1/12 pi. Take the derivative of h cubed. Well, chain rule, 3 comes down, h squared times the derivative of the inside, dh dt. Okay, good. So now we can solve. There's one other thing we haven't marked in our problem, but we now will, which is not only are we after dh dt, but when the pile is 4 feet high. Okay, so we now plug in h equals 4. So we get what? At h equals 4, we have that dv dt is 1/12 times pi times 3 times 4 squared times dh dt. And we can see that the 12 cancels with the 3 in one of the 4's. So that's 4 pi dh dt. Cool, cool, cool. But notice we know dv dt, it was given to us. So this is 12 pi. So 12 pi is 4 pi dh dt, which tells us that dh dt, well, 12 pi divided by 4 pi is 3. Good. Are we done? Are we over? No. There's one small last thing to do, because we want all the points. It's a good attitude to have, where we read in the instructions. Include units. Now, we don't have to include units in our work, but we do have to include it in our answer. So how do we figure it out? Well, the key is, what are the units of h? It's feet. So we say, okay, units of h, feet. What are the units of t? That's our time. What time scale? Seconds, minutes, hours, days? Minutes, because it tells us right there. So feet per minute. So the height is increasing at a rate of 3 feet per minute. That's it. We're done. Cool. Halfway. Woohoo! Well, of course, that means we have half to go. Woohoo! Okay, let's keep going. Number 5. Find the critical points of the function. F of x is 3x to the 4th minus 8x cubed plus 6x squared minus 1. And classify them as local maximum, local minimum, or neither. I read that in the wrong order, but okay, I got them all there. All right. So this is a find and classify critical points. Now, critical points relate to derivatives. And maybe if there are endpoints, but there's no endpoints here. And it's a polynomial, aka a nice function, the kind of function we wouldn't mind taking home to meet our relatives. So the key here is start with the derivative, f prime of x. Well, we can do term by term. That would be 12x cubed, 4 comes down, minus 24x squared, right? The 3 comes down, becomes a 2, and plus 12x to the 1, and the derivative of minus 1 is 0. Now, normally we start to be nervous because we see a cubic. But do we really? Take a look. Do these terms have things in common? They do. They all have 12x. So we'll pull it out. So we'll have 12x from the first term. We're left with x squared. The next term, that's minus 2x. From the last term is plus 1. Say, aha, we recognize that because we've seen things. And we remember things. We like it when we see things and remember things. So that becomes x minus 1 squared. Okay, so critical points. Never undefined, polynomial. When does it equal 0? Okay, so critical points. So that's when f prime of x equals 0. Well, that's when 12x times x minus 1 squared equals 0. And we see there are 2 places. So there are 2 critical points, 0 and 1. Now, if our question had been find, life is good. But there's also a question about classify. So, do we want the first derivative test or the second derivative test? And why do we want the first derivative test? Well, okay, good answer. We want the first derivative test. Exactly. Cool. Yes. The reason we want the first derivative test is that it's always conclusive. The second derivative test can be ambiguous, and I'm going to go ahead and tell you, and I'm not going to work it out, but I'm going to tell you that if you ran the second derivative test, you would get to the face that goes, because you'd have something where you wouldn't know what to do. Second derivative test would not be able to classify x equals 1. Go ahead and work it out, but for now, let's do first derivative test. And the idea of the first derivative test says, draw a line. Okay, that's good. Mark your points. Make sure you put them in order. Not too hard to do. 0 and 1. All right. Okay, what's so hard about that? Well, now pick values. So suppose I pick something like 2. And I plug it into the derivative. So 12 times 2 minus 1 squared. I don't care that the value is 24. I care about the sign. The sign will help us understand. The derivative is positive. Okay, between 0 and 1, say a half. 12 times a half, and then a half minus 1 is minus a half squared. Now, that's, again, we don't care about the sign. Sorry, the value, we care about the sign, right? Positive, positive, square, positive. So the derivative is still positive. Now plug in something like minus 1. 12 times minus 1 times minus 2 squared. Positive, negative, positive. Net result, negative. Okay, so what is this telling? We're figuring out the behavior of the function, and in particular, derivative is negative, we're going down. Derivative is positive, we're going up. So we see we are going down, we're going up, we're going up. So we say, aha, 0, this is a local min, because we went down then up. 1 is neither max or min. Because what happened? Well, we came in, we leveled, and then we went up again. So we had that motion, but we weren't a max or a min. All right, and so we can now summarize x equals 0 is a local min, and x equals 1 is neither. All right, good, done, done. Now, on a side note, the way I interpret this question, I'll tell you, there are people who might interpret it slightly differently. When I'm after the point, I'm after the x coordinate. Some people might insist x, y coordinate. Usually they will tell you x comma y. If they don't, I would say you're safe to assume just the x. That's my opinion. Don't get me in trouble. Please don't get me in trouble. If you wanted to, we can just mark what they are. When you plug in 0, 0, 0, 0, minus 1. Okay, that's not so hard. 0, minus 1. When you plug in 1, 3, minus 8, plus 6, minus 1, 9, minus 9 is 0. So 0, minus 1, and 1, 0 would be the xy version of the points. So, okay, we're done. On to the next problem. Number 6. Suppose f of t is a continuous function. All right, I suppose it. Good. Given that x sine of pi x is equal to the integral from 0 to x squared of f of t dt, find f of 4. Now, our first reaction is, huh? And then our second reaction is, oh, there's a hint. Let's read the hint. Hint, take the derivative of both sides of the equation. Okay. So on the left-hand side, we'd have a product rule. So the first times the derivative of the second. Well, the derivative of sine is cosine. We're going to have a pi come out by the chain rule. So x pi cosine pi x plus the derivative of the first, which is 1, times the second. Okay, so that's sort of the left-hand side. Now the right-hand side, we have an integral, and it has the x's in the bounds. So we're going to use two things: the fundamental theorem of calculus and the chain rule. So normally if it was just 0 to x, easy derivative. But 0 to x squared says, okay, the x squared is acting like the inside function. Because chain rule is an inside kind of job. So according to the chain rule, the derivative of f, plug the inside function in, times the derivative of the inside function. Okay, good. Now, that was the hint. How does that get us closer to the answer? Well, we're after f of 4. And there's only a single f, good news. And so we just have to plug in something that makes a 4. So we say, well, what's a value for x that works? Well, there's actually two of them. We could plug in positive 2 or negative 2. But because we like ourselves and because it's easy to lose track of signs, we're going to plug in positive 2. So we plug in x equals 2. And we get, we get 2 times pi times cosine 2 pi, which is 1. Good. And 1 sine 2 pi, which is 0. Okay. Cool, cool, cool. Is equal to f of 2 squared, which is 4, times 2 times 2, which is 4. Or, we could say, aha, f of 4, if we divide both sides, is equal to pi halves. Done, done. Wow. Amazing, amazing. All right, cool. Well, that's not so bad. The hint really helps that one. All right. Well, now what? Let's move on to part B. Okay, so part B. Suppose that g prime of x is equal to g of x, and g of x is continuous. Use the information in the table below, or using that information, find a such that integral from 1 to a to g of t dt is equal to 6. Okay, well let's, what can we do? What can we do? Well, if we think about it, they told us that little g is capital G prime. So if we think about it in that way, we'd say, oh, this is the same as 2 capital G prime of t dt. Now, why is that useful? Well, because it's easy to integrate a derivative. So that would be 2 capital G of t. I found the antiderivative of g prime. It was g. Easy to do that. And, okay. And we're going to evaluate 1 to a. All right. So this would be 2 g of a, plug in a, minus 2 g of 1. Okay, now do we know what g of 1 is? Well, we do. It's 0. Well, that's good. So what do we need? We need 2 g of a equals 6, or we need that g of a is equal to 3. So we start going through our table. We say, okay, is there a time when g of a equals 3? Ah, our eye gets drawn to the 3, right? It's not the input. We want the output to be 3. We say, okay, well, that corresponds to 4. So a will be 4. Done, done. Now, this is actually testing us again on fundamental theorem of calculus, because the key here is to understand, oh, I know how to take the integral of a derivative. Sometimes we're so used to it, we don't even realize we're using it. And, well, at that point, I guess you could say we've really mastered the tool. All right, so we've mastered fundamental theorem of calculus, and we got our answer. Good, good. Well, we're making good progress, just a few problems left. Let's finish it up. Number 7. Find the area of the region enclosed by the curves y equals 2x squared minus 3x minus 4, and y equals 5 plus 3x minus x squared. Now, I don't know exactly what they look like, but I know they're parabolas because they both have highest degree 2. I know this one is going to open up, smiley face, because positive coefficient. This one is going to open down, frowny face, negative coefficient. So I have something. I don't know. I'm just guessing. I'm probably very wrong. But at least I just am sort of saying, okay, all right, well, that's a picture to help get started. Now, how do we find the area? Well, we need to find where they intersect. So, that's step 1. Where do these two intersect? To find the answer to that, we say, okay, we know what the curves are, so we're going to say, when do they match? When does 2x squared minus 3x minus 4 match 5 plus 3x minus x squared? So we start moving things around, and by start moving things around, we'll just move everything to one side. So we'd have 3x squared, 2x squared plus x squared, minus 6x, minus 3x, and then we have a minus 9 equals 0. Well, divide everything by 3. X squared minus 2x minus 3 equals 0. Now, we're of course are like algebra. Yeah, we know algebra. So, we're looking for factoring. We're pretty optimistic that this will factor because after all, our calculus teachers like us. We're some of their favorite students. Okay, so what do we need? We need two numbers that multiply to negative 3 but add to negative 2. How about negative 3 and plus 1? Let's try that. Now, of course, as always, it's good to just double check because small mistakes happen, especially when it's late in the evening. X squared, okay, that looks good. Plus x minus 3x minus 2x is good. And minus 3. Check. Good. Okay, so that tells us that we're going to have intersections at 3 and negative 1. All right. So let's just say this is negative 1 and this is positive 3. All right. So the last thing for us to do is say, okay, what's the top and what's the bottom? Well, we already know the answer. The top curve is the frowny curve. So that's the second one. The bottom curve is the smiley one. That's the first one. Okay, so we know what the top curve and the bottom curve are. So here we go. The area is the integral from the first intersection to the last intersection, because they only intersect twice. We're going to take the top minus the bottom, dx. Well, if we work that out, so this will be 5 plus 3x minus x squared minus 2x squared minus 3x minus 4. And you might say, this feels really familiar. And it is. It's almost what we did, except it's going to be the negative, right? Minus x squared minus 2x squared is minus 3x squared. 3x minus minus 3x is plus 6x. And 5 minus minus 4 is 9. Now we go term by term. Okay, the integral of x squared. You add 1 to the 2, that gets us x cubed, and then you divide by 3. So I can think of it as 1/3 x cubed. Integral of x, add 1 to the exponent, that gives us a 2, divide by 2. And the integral of 9 is 9x. We don't need a plus c because this is a definite integral. We're definitely sure we don't need a plus c. Evaluate from negative 1 to 3. Okay, so cleaning that up, we have minus x cubed plus 3x squared plus 9x. All right, so we're almost there. Plug it in. When we plug in 3, minus 3 cubed is minus 27. 3 times 3 squared is plus 27. 9 times 3 is 27. Lots of 27s there. Subtract. Negative 1 cubed is negative 1 with a minus. Makes a 1. 3 times negative 1 squared is a 3. 9 times negative 1 is a minus 9. All right. Well, we can cancel some 27s. Doop, doop. You don't have to make the sound effect, by the way. You can just do it in your head. You know, it's a quiet, but okay. So, then being careful here, we could say, okay, we have 4 minus 9. So altogether, this would be negative 5. 27 minus negative 5. It's like 27 plus 5, which would give us 32. Aha, 32 what? Well, we don't know. We never assigned units to anything. But 32. 32. That's our answer. Life is good. Wonderful. Wonderful. Now, if you like this kind of problem, I've got some great news for you. Calc 2, advanced calculus, you're going to do so many more and cool things with integrals. This is just baby steps into what's possible. So much. I'm so envious of you. The whole world lies ahead. You're going to have so many cool things to discover. And, well, okay, that's for later. But for right now, let's finish this test. All right, one more to go. Number 8, our last problem. Woohoo! A group of researchers attached an accelerometer. Now, you can kind of figure out what this means. Acceleration, meter, means we're measuring. It's something that can measure the acceleration. And okay, so it's attached to a particle traveling along a line, and determine that its acceleration at time, any time greater than or equal to 1, was given by a formula. So here's our formula. At time t equals 1, the researchers measured the particle and found it was stationary, had no velocity, and was at the 1 meter mark. Find the equation of the particle's motion at time t greater than or equal to 1. All right, so what do we have? We know something about acceleration. We're after motion. Now, this is a slightly ambiguously stated question, and I'll be honest with you. What is motion here referring to? Because oftentimes motion might say, well, how is something moving? And so is that velocity or position? So here, I would say the right interpretation, and by the way, if you're ever unsure, there's a wonderful technique called raise your hand and ask during a test. Don't wait and ask after a test, because it won't help you if you ask then. So motion says we're after position. So once I know position, I know where I am at any time, and so that tells me how I move. Okay, so what's our idea? We have acceleration. We want position. Can we jump? No, that's a high jump. Well, what we can do is acceleration to velocity, velocity to position. So we're taking 2 steps. So we begin. So acceleration, we know, 1 over t squared. Now, I would write this as t to the negative 2, because that's a more calculus-friendly way. And then we have cosine pi t, and then we have units, which I don't worry about, because units, the nice thing about units is units work themselves out. They are what they need to be. So, how do I go from acceleration to velocity? Well, the change in velocity is acceleration, or if you like, the derivative of velocity is acceleration. So, to go from acceleration to velocity, I do the antiderivative, integrate. So, velocity is the integral of acceleration. Well, all right, that's the integral t to the minus 2 plus cosine of pi t. Now, here, because I've written it in a calculus-friendly way, so as a general rule of thumb, you write t to a power unless it's 1 over t. 1 over t is the exceptional case. All right, what will this be? Well, the rule says you add 1, so that's t to the minus 1, and then you divide by minus 1, which puts a minus. The integral of cosine, positive sign. Yes, 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 it's tricky to remember that. So it's a sine pi t, and the reason I say it's tricky is you say, well, is it a plus sign? Is it a minus sign? Well, you have to think about it. And it works the opposite in some sense as derivatives work. Now, you have to account for that pi. Now, you could do a substitution, u equals pi t, but oftentimes we see this so often, we say, well, if it's just constant t, 1 over the constant. Are we done? No. We need to add, of course, a plus c. Now, what is c? C is some constant to be determined. How do we determine it? Well, we use information. Now, sometimes we don't have information, it just stays as c, but this time it tells us 0 velocity. So I say, aha, cool. So, and that's at time t equal 1. So 0 is what happens when you plug 1 in. So we go through and plug in 1. So 1 to the minus 1 is 1. 1 to anything is 1. So we have minus 1. Sine of pi is 0. So that goes away. And then plus c. Well, that tells us that c should be plus 1. All right. So updating v of t. T to the minus 1. Again, I'm going to rewrite that back as 1 over t, because this is calculus-friendly way. It should be t to a power unless it's t to the minus 1, and then write it as 1 over t. Then we have our 1 over pi sine of pi t and plus 1. Okay, so we've successfully gone acceleration to velocity. We're halfway there. We now take our next step, which is velocity to position. Okay, so for whatever reason, physicists seem to use s for position. I guess they ran out of other letters. So that's the integral v of t dt. And, well, okay, so that's the integral minus 1 over t plus 1 over pi sine of pi t plus 1 dt. And we go term by term. 1 over t is log. Okay, now integral of sine is minus cosine. Yeah, pay attention. And now we say, oh, we have to account for the pi on the inside, so we have to divide by pi again, a second time. We already had a single pi, so now we're up to a pi squared. And then the integral of 1, don't forget that, is t. Are we done? No. We need a constant. Now, we've already used c. This is a different constant, so we use a different symbol. Work our way through the alphabet. Let's use the letter D. All right, so how do we find D? Well, how did we find C? We used information about velocity. So to find D, we use information about position. So what's our position? We were at the 1 meter mark. So at time 1, position was 1. So we have that 1 is equal to where we were at time 1, which is, plug in log of 1 is 0. Okay, so 0. And then we have minus 1 over pi squared cosine of pi times 1. That's cosine pi. Now, cosine of pi is a minus 1. There's another minus. That gets us to 1 over pi squared. Plus 1 plus d. Well, we see that the 1's cancel. And that leads us to the conclusion that d is minus 1 over pi squared. So finally, we get that our position, which is telling us how the particle moves, because it gives us the location at any given time, is minus log of t minus 1 over pi squared cosine pi t plus t minus 1 over pi squared. And we're done. Our final problem. Ah, wow, we made it all the way through. Woohoo! Nice. All right, well, good job us. I'm glad we stayed to the end. Wonderful problems. I hope you enjoyed it. I hope you're ready. Your test, because it's cumulative, who knows? Who knows what's going to be on the test? But you'll see common themes showing up again and again. And so it's good to go back and look at these old exams, practice them, do them until you're comfortable, because that'll greatly improve your odds that you can do the one that you'll be faced with. That finishes it for today. I hope you do well, and I hope I get to see you again. Bye.